So now we are moving towards the next example, example number 11. Example number 11. So consider any field. So at this moment it is not very correct to say field if you don't have any knowledge of field, but for me this notation f means the set of rational numbers, set of real numbers, set of complex numbers, and actually there are many more fields, but we know all these three fields. So whatever I am going to define for f, you can consider it for q, r or c. So now consider the two numbers mn, natural number, take, and define a set m cross n f. This means the set of all matrices Aij of order m cross n matrices such that these entries Aij belongs to the field F. So you may take it in Q, you may take it in R, you may take it in C. Entries you can take from rational numbers, real numbers or complex numbers, or any other field if you know. So this is the set of all m cross n matrices over F. And we know how to add two matrices. So define plus from m cross nf cross m cross nf to m cross nf as, so if I take two matrices Aij, m cross n, and I want to add with another matrix Bij, which is also of size m cross n, then we define it as the entry wise addition Aij plus Bij m cross n. So you will get a new matrix after adding. So this is nothing but the addition of two matrices. You know it very well. So addition of matrices is a binary operation on the set of all matrices of size m cross n. So if you will add two matrices of size m cross n, you will again get a matrix of size m cross n. So it is a binary operation. And one more thing, there is a matrix 0 matrix m cross n. 0 m cross n is a matrix of size m cross n, such that all its entries are 0. Everything is 0 here. So this is a 0 matrix, and this 0 matrix belongs to the set of all these matrices. Now, one thing we can see that this set of matrices, this operation of addition of matrices, if I take three matrices Bij, m cross n, and take another matrix Cij, that is, by definition of the sum of matrices, you can always write it as Aij plus Bij plus Cij m cross n. So just keep in mind, this is a number, this is a number, this is a number. Number means elements of the field, and this bracket means the matrix. So this whole is a matrix. So by the definition of addition, we can do one thing. This is the addition of integers. Addition of numbers means elements of the field, and that addition is always associative. So this we can write it like this, m cross n, and this is Aij, m cross n plus Bij plus Cij m cross n. Further note that this is a matrix, and this is Aij m cross n plus in bracket Bij m cross n plus Cij m cross n. So it means simply that this operation of addition of matrices is a associative operation. And when will you add this zero element to any matrix, what will happen? So take an element Aij m cross n in the set of all matrices, and let me add 0 with it. So Aij m cross n, we add the 0 matrix m cross n. Then what will we get is that Aij will be added with 0. This is 0 of the field, and when you will add 0 with it, you will get Aij m cross n. So this element is working as an identity element. So you may say that this is a semi-group with identity. And what about inverse? So if I take any matrix, so now if I take Aij m cross n in m cross n f, then it is clear that minus Aij m cross n is also a matrix in m cross n f. And when we will add these two matrices, Aij m cross n with minus of Aij m cross n, we will get Aij minus Aij m cross n. So it means 0 m cross n. So that is nothing but the 0 matrix of order m cross n. So it means this element is the inverse of this. So this matrix is the inverse with respect to addition of matrix for this matrix. So inverse exists. So it means this set m cross n f with respect to addition of matrices, this is a group. This is a group. This is a group. This is a group. Okay. So the set of all matrices with respect to addition, m cross n matrices over the field F with respect to addition forms a group. As we have done this, on the same way, we can also show that if I take a set of all symmetric matrices, that is, let me give some name S to this set, those A in M. So for symmetric matrix you need to take a square matrix. So suppose I take it like this, such that A is equal to A transpose, then you can show that the sum of two symmetric matrices again is symmetric matrix, and I am leaving it as exercise that show that this is a group. Similarly, the set of all skew symmetric matrices is a group. Set of all skew symmetric matrices on skew symmetric. So this is an exercise for you to show that. So let me write it properly. One second. So exercise, show that first set of all skew symmetric matrices is a group with respect to So this is with respect to addition. So this sentence is actually set of all skew symmetric matrices of size n over a field F is a group with respect to addition. Similarly, you can show that set of all upper triangle matrices I am not writing it completely. Set of all upper triangle matrices is a group with respect to addition of matrices. Third, set of all lower triangle matrices. This is also a group with respect to addition of matrices. And then set of all diagonal matrices. Set of all scalar matrices. These all are groups with respect to addition of matrices, and there are many more groups in this set also, which we can define. For example, strictly upper triangular matrices, strict lower triangular matrices, and so on. So, this is exercise for you to verify that these are groups. Okay. Now we are going towards next example. So now we are coming to our next example, example number 12. And this is the general linear group. So again, fix a field F. So that field for you can be R, C or Q, anything. Or if you know more fields, then you can add the field you want. And then define a set. So first fix a n in n. Let me fix it. And for this n, let me define a set GLNF. This is the set of matrices, those matrix A in the set of all n cross n matrices over F, such that the determinant of A is not equal to 0. Those matrices whose determinant is not equal to 0. So now one thing is that if I take A matrix capital A such that determinant is not equal to 0, and I take another matrix B such that determinant of B is not equal to 0, then you know that determinant of A into B is equal to determinant of A into determinant of B. And if this is non-zero, this is non-zero, then their product will not equal to be 0. So this implies if A, B belongs to GLN F, then A to B also belongs to GLN F. So means the product of two matrices of this set is again a matrix of this set. So it means the multiplication is a binary operation on this set. So we can define the multiplication operation, which is a binary operation. So define dot from GLNF cross GLNF to GLNF, and that is the matrix multiplication. This is operation is matrix multiplication. So GLNF with respect to the matrix multiplication operation, this is a group I. And now it is not hard to see that the matrix multiplication is associative operation, means if I take A, B, C, three matrices in GLNF, then A into B into C is equal to A into B into C. It is not very hard to see. So I am leaving it for your verification, that show that A dot B dot C is same thing as A dot B dot C. Okay. So this is the associative boundary operation. It means this is a semi group. Now, determinant of identity matrix n cross n identity matrix is 1, which is not equal to 0. So this identity matrix belongs to GLNF. And when you take any matrix in GLNF and you multiply it with identity matrix, you will get the same matrix. So it means IN is identity element of GLNF. One more thing which we will use is that if I take any matrix A in GLNF, then because determinant of A is not equal to 0, so there exists a matrix A inverse such that A into A inverse is equal to A inverse into A is equal to I n cross n. I think this you know, that if the determinant of a matrix is non-zero, then there exists an inverse of the matrix, and that inverse is actually the adjoint of A upon determinant of A. So, okay, so inverse exists, and because determinant of A is non-zero and A into A inverse is identity, so if we will take determinant function on this side, then the determinant of A into A inverse is determinant of identity, that is 1. So it means determinant of A into determinant of A inverse is equal to 1. So this implies determinant of A inverse is not equal to 0. So it means inverse belongs to the set GLNF. So this implies that A inverse belongs to GLNF. So inverse of each of the matrices of GLNF is in GLNF. Hence GLNF with respect to multiplication of matrices, this is a group. This is a group. So now next example. So I think it is okay for you. Now next example is a special linear group. A special linear group. SLNF. This is the set of those matrices of GLNF such that determinant of A is equal to 1. So one thing is clear, that this is a subset of GLNF. So because the associativity with respect to multiplication is there in GLNF, so associativity of multiplication is also there in SLNF. And one more thing, if I take AB in SLNF, then it means the determinant of A is equal to determinant of B is equal to 1. Then what about the determinant of AB? By the definition of determinant of AB, it is equal to determinant of A into determinant of B. So it is 1 into 1, so it is 1. So this means AB also belongs to SLNF. So SLNF with respect to multiplication forms a semigroup. So SLNF with respect to multiplication, this is a semigroup. Why? Because product of two matrices of a special linear, this set SLNF, is again an element of SLNF. So this dot is a boundary operation on it, and because SLN is a subset of GLNF, and on GLNF multiplication of matrices is associative, so on SLNF multiplication of matrices is also associative, so it is a semigroup. One more thing, that the determinant of identity matrix is 1, so IN belongs to SLNF. So SLNF has identity also. Now also, if A is in SLNF, which is contained in GLNF, so A inverse exists, and A inverse exists, so at least in GLNF it has inverse. But what about this? This is determinant of IN, this is 1, but this is same thing as determinant of A into determinant of A inverse is equal to 1. So this implies 1 into determinant of A inverse is equal to 1. So this implies determinant of A inverse is 1. So inverse matrix has determinant 1. So this implies A inverse belongs to SLNF. So if A is in SLNF, then inverse is also in SLNF. So it means SLNF is a group. And that group is called a special linear group. So we can say that this SLNF is a group. So SLNF is a group with respect to multiplication of matrices, and that is called a special linear group. Sometimes GLNF is also written as GLNF. So don't be confused with it. And similarly, SLNF is also written as SLNF. So please don't get confused with it. Both are notation for it. Okay. Now there is one more example. And that is orthogonal group. So this is usually noted as ONF. Some people also write it as ONF. So how is it defined? This is set of those matrices in GLNF such that A into A transpose is equal to A transpose into A is equal to identity. Clearly, if A and B belongs to ONF, then A into A transpose is equal to identity, and B into B transpose is also equal to identity. Now what about AB into AB transpose? Now where A dot B is the multiplication of A and B. So this can be written as AB, B transpose, A transpose, because after taking the transpose it will become B transpose into A transpose. And matrix multiplication is associative, so we can take first the product of these two matrices. B into B transpose is identity, you know. So we can write A into identity into A transpose, and now this is again A into A transpose, so it is identity. So it means AB also belongs to ONF. So matrix multiplication is a boundary operation on ONF. So ONF with respect to matrix multiplication is a groupoid. So ONF with respect to multiplication of matrices, this is a groupoid. Now one thing one can observe that In belongs to NF because In transpose is In and In into In transpose is In again. So this is the identity. Okay. So identity element belongs to it, and also if A belongs to ONF, then this implies that A transpose also belongs to ONF. But note that by the definition of A transpose is actually equal to A inverse. So inverse of each of the elements belongs to ONF. So ONF is, with respect to matrix multiplication, this is a group.